This is a demonstration of the test bench used for the localization and mapping of the MECH5080M team project, which is investigating the feasibility excuse me, of an automated underwater vehicle. Specifically, it's an automatic submersed wheeled robot that drives along the bottom of the riverbed and collects samples at various points to assist with alluvial deposit detection and various other items. So this is specifically the localization and mapping test bench. I'll just quickly take you through it. So we have a Raspberry Pi 4B here, which is the main compute, chosen basically because it was quite easy to program on, has a native file system, easy to get data in and out. We have an accelerometer here, the BN0055 specifically, on a breakout board that they use for testing. We have a GPS here, it's B180, it's just a cheap drone GPS because the more expensive one broke. And then we have over here what's used in the mapping system, which is a Raspberry Pi Pico, which is the controller for this system here and performs various other rotations to minimize the impact on the main controller when collecting bathymetric data, which is just water depth. So you'll notice this is not submerged, and that's unfortunately due to the lead time of components. So we're using analogous on-land components, which I'll take you through. So for example, with this GPS, we have an underwater GPS, I forget the name of it now, but it's useful up to 300 meters. You have one that goes in the top of the water and then one which goes in the actual submersible vehicle. And it's accurate, it's very accurate and up to 300 meters and is incredibly expensive, but just hasn't arrived in time. We also have the two servos here, which are just parallax servos, and originally we are going to use ROV Maker high torque servos. Once again, haven't arrived in time. And then we also have an HC SRO4 ultrasonic sensor, which just measures distance, which we were going to replace with the Blue Robotics ping sonar, which is slightly more accurate than this sensor specifically. I mean, this is £4 and the ping sonar is about 360. But works for actually testing the software implementation here. So the localization system, just get this up and running now. So you can see the bathymetric thing going. So the localization system uses an accelerometer, which is we're getting our orientation here. It's a 9 degrees of freedom sensor. We're getting our orientation from here as well as our linear acceleration, which discounts gravity. And this is being corrected by a Kalman filter within the main controller periodically to minimize the error and the uncertainty of these measurements. We also then correct that further with this GPS chip, which uses Bayes' theorem to combine the probabilistic estimates of position to give a absolute point in space for this main controller. Unfortunately, this corrupts too quickly to provide an accurate estimation of space. It would be interesting to see if the more expensive submersible components would have provided the better alternative, but I think largely it's due to a lack of throughput from the bathymetric system, which we were going to use in an EKF SLAM implementation. But that does bring us nicely along to the bathymetric system. So here you can see this moving along. This is an actuated distance sensor, so this is getting a distance from this point every time it's taking a measurement. And this is controlled by this Raspberry Pi Pico. And the reason that this is controlled by the Pico, not directed by the main controller, is that it was required to be, is going to be physically separated on the actual device within the chassis. It has to perform time-sensitive measurements, as in this is running a Linux non-deterministic OS, and it's required to it's required to take the measurements and correct them in real time, and we want to minimize the impact of that on the main controller. Is the main control sensor position command, which this then adjusts to, tells it that it's positioned. The main controller then checks that, because there are going to be multiple ping sonars operating at the same time, it then checks that there's not one transmitting with the same frequency. If this is the case, if this isn't the case, then and it's good to transmit, it just tells it where to transmit, and also sends an absolute pose at that same point. and this device then takes that ping measurement as a one-dimensional distance. It then uses its digital twin copy of these position of these two servos, combined with the absolute pose of the main controller in space, and it creates an absolute point where this has reflected from, and then sends that back to the main controller, minimizing the work required. Unfortunately, you can see from this that even at short distances, because this is heavily affected by the time of flight, even at short distances, the data throughput is really slow. And this was the idea behind this was that we would mitigate the very expensive side scan and multi-beam sonars that are used in SLAM implementations and submersible vehicles through this actuated mechanism, and then correct our localization with SLAM, but unfortunately this corrupts too quickly for this to remain accurate to then be used with a SLAM implementation to update the localization. However, we do think that with additional data throughput, this could become incredibly feasible.